Did you know that Toy Story from 1995, as the first fully animated movie in history, did not use any of the advanced rendering techniques that existed at the time, including ray tracing and path tracing? It was all done using rasterization-based techniques, and it took them around 800,000 machine hours of rendering, or around 6 hours per frame, which, with around 50 to 100 computers, was almost one whole year worth of time. If we take a look at Lumen today, 30 years later, we could render the entire movie in real time, with each frame taking about 5 milliseconds on a high-end setup. However, the traditional ray tracing and path tracing that shoots a ray from the camera through the pixel is still not used, even in this case for game engines. So, what is going on? You can guess that the main reason is the performance efficiency, but what ideas led the people in the computer graphics community in the 1970s to strive away from rasterization-based techniques and introduce ray tracing, and how Lumen relies on it, but not in the way you think? Hey, my name is Marco, and I'm trying to understand how Lumen works, and in this video of our Real-Time Global Illumination lecture series, we're continuing our journey from the fundamentals of basic lighting and rasterization that we did in our previous video that you can check out here, and exploring what led to the fundamental shift in how we process our 3D geometry to 2D images in the scene. We will cover the concepts of ray tracing, path tracing, importance sampling, and deferred rendering before seeing how this all fits together with Lumen, so stay until the end to find out. But before we talk about our topic today, we can ask a question. What does it mean to trace a ray? In real life, rays are shot from the light source, and let's say we trace them, hoping to find out what the camera sees. The problem here is that most rays go everywhere else. You do a lot of work for almost no payoff. Instead, we do the opposite, starting at the camera and ask, what am I looking at? This guarantees every ray contributes to a pixel, which is a much more efficient approach, but how do we get to it? Well, when we last talked about rasterization-based approaches, we said that we can generate a Z buffer to check which parts are visible and which are not. This was introduced back in 1974. However, 6 years earlier, in 1968, Arthur Appel had the same visibility issue he wanted to solve when he introduced the concept of ray casting, which is a concept when you shoot the rays from the camera and then check the closest intersection with the primitive. He did not know it at a time, but this was a game changer ahead of its time. So why is it so? Well, look at it like this. In rasterization, you had an approach that for each primitive, you should find the pixel sample. However, now in ray casting, you had an approach that for each pixel sample, you should find the closest primitive. At the time, the computational power was not there, which is why this concept was applied almost a decade later in 1979, when Turner Whitted proposed such a solution in his seminal paper, where instead of processing triangles directly, this approach traced rays through the scene. In essence, that meant a fundamental shift in how things were done. This reverse approach allowed for realistic shadows, reflections, and refractions, which was previously impossible in rasterization without hacks like shadow mapping and cube maps. This is Whitted's first ray-traced image, a 512 by 512 rendering featuring spheres, shadows, reflections, and refractions, and it took them 74 minutes to compute per frame. But how does it actually work? Well, we shoot out the rays from the camera, implementing the ray casting approach. These rays are called the primary rays. However, when a primary ray hits a surface, another ray is drawn from the intersection point to the light source in order to verify whether the object light is illuminating this part of the geometry. These are called shadow rays. If the shadow rays reach the light without intersection, then the pixel is colored by the diffuse and specular highlight colors based on the material information. However, if the part of the geometry is in shadow, it is assigned an ambient color. Furthermore, if the surface is reflective, the ray bounces off the geometry elsewhere in the scene based on the angle of incidence. If it encounters another geometry, the color of that pixel will be influenced by this reflection. Since we draw a lot of these secondary rays and the same procedure is repeated, this makes this procedure a recursive ray casting process. The procedure, of course, gets more complicated if the rays are refracted when we use the index of refraction to calculate the light direction after the intersection. So you can see that this whole procedure requires a lot of calculation. But just how much is that? Well, a single ray must check for intersections with all scene primitives, which can result in a lot of misses. So with around 2 million pixels for an HD display and 1,000 triangles, which is pretty low for a scene, we can reach over 2 billion calculations for each frame, which makes this process extremely time-consuming. So instead of testing every primitive with ON of complexity, we use a bounding volume hierarchy, or a BVH, to divide the scene into hierarchical bounding boxes. By quickly eliminating large groups of objects, BVH reduces intersection tests to O of logarithm of n, significantly improving performance. So instead of having 2 billion checks, we can boil down to 50 times less. This same optimization is used in Unreal Engine's Nanite, which we covered in our previous lecture, which you can check out here. However, in traditional ray tracing, only one ray per pixel is cast, which results in aliasing or jagged edges and sharp transitions. This happens because only the pixels whose centers are covered are the ones that are shaded. So, can we shoot multiple rays per pixel, and by doing so determine the final color of a pixel by averaging all the sampled rays? This is the exact question Rob Cook and his team had in 1984 when they introduced distributed ray tracing, where multiple rays are cast per pixel with randomized offsets that allowed for anti-aliasing or the reduction of jagged edges, but also other effects such as motion blur and depth of field, as you can see in this image. Regarding shadows, shadow penumbras or soft shadows can be generated by sending multiple shadow rays per shading point, not through a pixel, when sampling an area light. But this idea, taking multiple random samples and averaging the result, isn't just used in rendering. A similar concept had already been developed decades earlier in a technique called Monte Carlo approximation. So Monte Carlo methods originated in the 1950s, providing a way to approximate complex problems using random sampling. Imagine we want to determine the area of this quarter of a circle with a radius of 1 unit. We can randomly scatter points inside the square whose sides are of the same radius as the circle. Some of these points will fall inside the quarter circle, while others will land outside. If we take just a few samples, our estimate will be inaccurate. But as we increase the number of samples, the ratio of points inside the circle to the total points we have will approach 1/4 of pi. Well, Cook's stochastic ray tracing follows this same principle. The more samples we take, the better the result, but at the cost of more computation. If this is too complicated to understand, we can have a different analogy. So imagine trying to figure out how sweet a cake is by tasting just one bite. One bite might have all the frosting or no filling at all, but the more bites you take from different parts of the cake, the closer your average score is to the true sweetness. That's Monte Carlo sampling of this Monte Carlo cake. Averaging random samples to estimate a complex whole. Now, even though Monte Carlo sampling allows us to generate soft shadows, reflections, and realistic depth of field, there's still something missing. In the real world, light doesn't just hit an object and stop, only based on reflection, refraction, and light exposure. It bounces around in the scene and from other objects in the scene. So without this effect, shadows appear too dark and the scene lacks realism. Now the scene on the right seems more realistic, and it's because we have indirect light or bounced light present. Light that reflects off walls, ceilings, and objects, softly illuminating the space and creating those green and red tints that bleed from the walls, diminishing the harshness of the shadows. So, how can we make this happen? Well, we need to introduce the concept of global illumination, or GI, which refers to the way light interacts with the entire scene, including both direct and indirect illumination. And in 1986, James Kangia introduced a concept for it in his seminal paper called the rendering equation, in which he introduces a mathematical model that describes how light interacts with surfaces. So let's check it out. This is the rendering equation as originally published in the paper. So if you've never seen it before, it looks pretty complicated to understand and grasp, especially if you were a beginner. So for starters, let's write it in this shorter form and consider how we can go about understanding it. Let's go back to the only equation we've used thus far, the Phong material model, which we talked about in our previous lecture, which is used to calculate the color of the pixel based on the light intensity, geometry term, material coefficients, and the ambient term, which, if you remember, was introduced as a hack to fake indirect lighting. But let's focus on this part here that had to do with material properties, the diffuse lighting, and specular highlights. We had this diagram explaining what angles were introduced based on the incoming light ray omega and the viewing ray v. But since we want to find a way to calculate the outgoing light from the surface in order to see its indirect contribution, we can exchange the light ray L and the view ray V with the incoming light ray omega I and the outgoing light ray omega O, and create a function that includes these variables based on the angle between them. Based on the two directions, we can call this function the bidirectional reflectance distribution function, or the BRDF, which we have covered in our previous lecture, that basically tells us what is the percentage of incoming light that will be reflected to the camera along the outgoing direction. Since this function returns a number that should not be more than 1, we still don't have the light information, which means that we need to include the incoming light intensity or irradiance in the calculation, but also the cosine distribution or the geometry term we talked about earlier. And now we have a way to calculate the outgoing light from a specific point on a surface based on the incoming light, the geometry term, and the BRDF, which is based on material properties like normal distribution, Fresnel reflections, and the masking function, which we already talked about in one of our previous lectures. Now, this looks fairly similar to the Phong material model we've used previously, but there's a catch. This way of calculating only takes into consideration one light source. If we introduce multiple light sources, we should annotate that in the equation by adding the sum of all incoming light rays for that specific point on a surface. However, this still assumes we are only dealing with direct lighting and all light contributions come from a finite number of sources. But in reality, light bounces multiple times coming from all possible directions. So to account for this, we need to generalize our model. And since light can come from any direction, we replace the sum with an integral over the hemisphere, which we annotate with the capital omega symbol, and we have an equation we started from, which is the rendering equation. Now, we can also add the emitted light contribution, and now hopefully you can understand why this equation is written as such, and we can rest assured that we finally have a mathematical model to calculate indirect lighting. So, indirect lighting, here I come, right? Yes, but actually no. You see, the rendering equation is almost impossible to solve in a closed form solution because you cannot account for all the incoming light in a straightforward way. So, what can we do? Let's check out this simple example. If we wanted to calculate the integral, which is basically the area under the curve, and the curve has a well-defined function with known properties, we have the way to do it and we can get an accurate result like we see here. But if we couldn't solve the integral because we don't know its function, like in our example in the rendering equation, we could try and approximate it with a finite set of samples, which is a similar thing we did in the Monte Carlo method we mentioned in the distributed ray tracing from Cook. And by adding more and more samples, we are getting closer and closer to the accurate result. And with 100 samples, we are not there yet, but are close to it. So let's add more. If we add 1,000 samples, the results will be fairly accurate and the area under the curve would look like it approximates the final result very closely. But does it? If we zoom in very, very close to the curve, we can see that there are still some pieces of the area missing, but at least we have a starting strategy for solving our rendering equation integral. Try to solve it using Monte Carlo approximation with a finite number of samples. So on a practical note, that would mean that if we were to take only one pixel from our final image and shoot a ray through it, we could bounce the ray off in different random directions and get an estimate of what the indirect light contribution is for this ray, but only if it reaches the light source. Since we are tracing the values along the path, this approach is called path tracing, but that would only be one sample. So since this is not enough, we can shoot different rays from the same first hit point to try and accumulate more light information, which can get pretty computationally expensive, even for 10 samples shown here and 4 bounces along each path. And lastly, we can also sample through multiple different samples instead of just one point on the pixel, making even more rays for determining the indirect light contribution of a diffuse material for this pixel. So with 10 different sample positions on the pixel and 100 rays in total, this has to be enough to approximate the result, right? Well, our 100 samples per pixel looks like this, which is very, very noisy, and by adding more and more samples, almost doubling the amount in each iteration, we're getting better and better results, even reaching 400,000 samples for a single pixel. Now that would mean that for an HD image, it would be almost 800 billion rays. Now let's pause for a second. If we continue sending out rays randomly across the hemisphere at every bounce, we quickly run into two problems. First, we're wasting time on rays that contribute almost nothing. Maybe they miss the light entirely. And second, we're tracing paths that could bounce 5, 6, or even 10 times, all for a pixel that barely changes. That's a lot of computation for very little reward, which is why we need to work smarter, not harder. So how can we do that? So here's the first idea. What if we could probabilistically stop the low impact rays? So let's say we shoot a ray and after a few bounces, let's say 3, look at how much radiance the path is still carrying. This value is called the throughput. It's an RGB value that represents how much energy the ray has accumulated so far. To decide if the ray should continue, we need to convert that color into a single scalar probability between 0 and 1 that is called the survival probability. We then draw a random number between 0 and 1, usually denoted as Xi, and if Xi is greater than the survival probability, we terminate the ray. So end of the path. But if Xi is less than or equal to the probability, we let the path continue and we scale its contribution by the inverse of that probability. This keeps the overall estimate unbiased. So for many samples, the energy that was lost by terminating weak paths is accounted for by boosting the ones that survive. And this allows us to avoid wasting resources on low energy rays while still converging to the correct lighting results. This was the idea of Russian Roulette path termination that James Kajiya had in his paper as a way to solve the rendering equation. But he also proposed an alternative one. So let's check that one out. So now we've solved one part of the problem. We've stopped wasting time on rays that contribute almost nothing. But the areas that require the longest light transport path exhibit the most noise, which still leaves us with another challenge. So let's say a ray does survive. It bounces off a surface, and now we need to figure out how much light is coming from that direction. So we randomly pick another bounce direction on the hemisphere. And again, we hope it leads somewhere useful, maybe towards a light or maybe not. So for diffuse materials and for 100 rays following a uniform random direction on the hemisphere, we can get a very noisy output. But what if instead of hoping, we ask a direct question? From this source point, can I see a light source? Since we are sampling a light source, we do some manner of importance sampling because we give more importance to certain light rays that will contribute to the overall illumination. However, if we use it with a single bounce, we basically get direct lighting, like we did here, but can it be used for indirect lighting, so with multiple bounces? That's the idea behind next event estimation. At every location that a pixel sees, we place a hemisphere onto which we project all the light sources that can contribute to lighting. Now, we know where to shoot our rays that can contribute to the lighting information. If we shoot secondary rays towards these areas, we are highly likely to get a lighting information which is similar to sending shadow rays for direct lighting. Now, if we shoot random secondary rays and then generate additional shadow rays checking if there is a clear line of sight to the light, we can add the lighting contribution. Of course, if the shadow rays is blocked, we don't add anything. This massively reduces noise from direct lighting, especially when light sources are small or far away. Instead of waiting for a lucky random bounce to reach the light, we just check if it's visible and add its effect immediately. But as you can see, there's still some noise, and the computation time is still very large. Now, we can implement better sampling strategies, but the bigger question is it just the sampling methods that's inefficient? Or is the whole way we're rendering the scene? So back in 1986, when James Kajiya introduced the rendering equation, the standard rendering approach in real-time graphics was forward rendering. And it's simple. For every object in the viewing frustum, you compute how a subset of lights affects it and draw the final pixel color right then and there. But this meant doing lighting calculations for everything in the viewing frustum, even if most of it wasn't visible. So for a scene like this, where you have some cubes in front of the others, the procedure in the rendering pipeline would be like this. We render every mesh pair with every light and then just discard the result if the Z buffer data indicates so. Now, forward rendering is the only way to go when you have transparent materials because you need to know what is behind each mesh. However, this approach is incredibly inefficient as scenes get more and more complex or contain more lights. And the question lingers, why compute lighting for a surface that's behind a surface? Why shade a pixel you'll never see? So, what if we render geometry first, storing only what's visible in a screen-aligned buffer initially known as the super buffer, but now referred to as the geometry buffer or the G buffer, and then compute lighting only for those visible points? In 1990, Michael Deering and his colleagues had this exact idea, introducing the concept that will later be known as deferred shading, which changed everything when it comes to rendering complex scenes with multiple lighting. So the G buffer stores essential information for each pixel like depth, surface normals, albedo, roughness, and similar, which we use to compute direct illumination or how much light hits the surface directly from visible light sources. And this means the GPU doesn't have to trace rays or shade invisible surfaces. It just uses this data to light what's actually on the screen. And this includes both diffuse shading and specular highlights. Now, shadowing is added using shadow maps or ray traced shadows, which can also be softened by sending more samples to area lights. And this part is a separate module, independent of other rays, which is one benefit of using the G-buffer. But direct lighting alone is not enough. Realistic scenes include indirect illumination, so light that has bounced off other surfaces before reaching the viewer, which is also added as a separate module to the G-buffer. So once all the individual passes are computed, from direct light and shadows to indirect bounces, they're combined to produce a final image that approximates global illumination. And all of this is possible without retracing visibility because the G-buffer already gave us the visible geometry, making it easy to render scenes with dozens or even hundreds of dynamic lights, since we could loop over lights per pixel instead of per object. But the G-buffer isn't perfect. It's limited to what the camera sees, meaning it doesn't account for objects just outside the screen, or hidden geometry that still affects indirect lighting. It also struggles with transparency, since multiple layers per pixel can't easily be stored. And the more data we store in it, like velocity, ambient occlusion, or material IDs, the more memory and bandwidth it consumes. So we can improve performance by integrating a deferred rendering pipeline, but what if the directions we're sampling for bounce lighting are still random and not well distributed, which still leads to noise even when we use a lot of samples? Now we can explore this as another important sampling concept, but draw our attention to the BRDF, or the material properties that reflect and scatter the light based on their roughness and glossiness following the reflection lobe. So for shiny surfaces, we shoot more rays towards the dominant BRDF lobe area in order to optimize the amount of samples and their distribution along the hemisphere. This is what we call important sampling, where we sample the BRDF. Now, if we were to shoot rays equally in all directions following a more uniform scattering, ignoring the BRDF lobe, we would get noisy results since less sample rays are allocated to important directions. But the BRDF can be different for purely diffuse materials that scatter and reflect rays in all directions, which means that if we do important sampling of the BRDF, like in the case on the left, we are losing a lot of lighting information. So what can we do? So that means that we need to prioritize both importance BRDF sampling cases for both diffuse and the specular materials in order to get a good result. But we also need to sample the light as well. So what is the best solution? So this is the exact question that troubled the computer graphics community for years, until Eric Veach suggested a multiple importance sampling approach where you can shoot out the rays based on both BRDF and light, with them averaging according to heuristics. You can see more about the issues of each single importance sampling, so for light and BSDF in this case, the bidirectional scattering distribution function, and how combining them gets a more realistic look or a result with less noise and less light rays. But this is a static strategy. Each sample is chosen without knowing whether it will actually help. Now, we've covered a lot so far, from ray tracing and path tracing to importance sampling in various formations. But all of this lives in the world of offline rendering, sorry for all caps, where you can afford to take hundreds of samples per pixel and where you can wait minutes or even hours for the perfect frame. But Lumen runs in a game engine, Unreal Engine 5. That means it has to do all its lighting in milliseconds, not minutes. So full path tracing, thousands of rays, or multiple light bounces per frame, none of that is practical. The system has to be smarter, leaner, and built with real-time constraints in mind. Because of that, Lumen doesn't shoot primary rays from the camera at all. It relies on the G-buffer, just like we saw in deferred rendering and we mentioned in the previous video. It uses rasterization-based techniques. So the expensive step of finding the intersection between primary rays and surfaces and figure out visibility, already done. So no ray casting from the camera. What Lumen does trace are secondary rays for things like indirect lighting or reflections, but not for every pixel. According to Daniel Wright, one of Lumen's architects, we can only afford half a ray per pixel, which is very little when you see that you need at least 100 for outdoor and around 500 for indoor scenes. So we have to get even better with choosing the direction of our rays. And how does Lumen do this? Lumen uses ray guiding, which is a very real-time friendly way of doing important sampling, just shooting rays where they matter most. This concept existed in the 1990s but was abandoned due to bottlenecks that disappeared in 2014 when Jiří Vorba and his colleagues were among the first to revive the process as path guiding. And many colleagues joined in, like Sebastian Herholz in 2016, and in their approach, the renderer builds a directional model of where useful light is coming from using a structure that improves as more paths are traced. This guidance works within a single frame, but it becomes far more effective when accumulated over time. So instead of calculating importance from scratch each frame, it caches the current lighting information, reuses it for subsequent frames, and interpolates in between the pixels that have lighting information already calculated. This cache guides future rays without recalculating the whole hemisphere. And one such asset that can handle real-time diffuse global illumination is H-Trace, created for the Unity game engine and developed with Pavel Vorobyev as part of the development team, who has offered his time and expertise to improve this lecture for all the community members and share the knowledge for all the important topics that are integrated into Lumen. So if you would like to show support to him, share the knowledge or use H-Trace in your workflow. And if you would like to support me in researching all these topics, consider liking the video or write a comment about what information or approach you found most interesting, or which topic can benefit from additional explanations. So Lumen needs a way to store lighting intelligently, reuse it, and avoid tracing unless absolutely necessary. It needs a system that understands what parts of the scene are likely to stay lit and where to sample next. And in the next video, we'll dive into how Lumen handles this real-time global illumination and caching process, and how it stores and interpolates lighting using techniques like radiance caching, surface cards, and lighting probes. We'll see how all these parts, G-buffer, ray guiding, and smart sampling fit together into a hybrid system that's efficient enough to run at 60 FPS, but grounded in decades of rendering research. I thank you for your time and hope to see you in the next video. Bye.